So we know in the air the index of refraction is 1. That means the speed is 3 times 10 to the 8th meters per second. The 640 nanometers is 640 times 10 to the minus 9th, right? And then we can find the frequency, and it's going to be in the boogala hertz range, right? And the frequency is just going to be velocity divided by wavelength, right? And so I'm using the formula V is F lambda, right? So 3 E8 meters per second, and how many of these fit in there? 640 nanometers. Well, it's going to be a lot, right? Yeah. So 3 times 10 to the 8, 3E8 divided by 640 E minus, and that gives me the frequency is 4.6875 times 10 to the 14th hertz, which is, technically speaking, that's boogala hertz, sorry, right? And then down here we can talk about the velocity, we can talk about the frequency, we can talk about the wavelength, right? And one of these is going to be the same, either the velocity, the frequency, or the wavelength is going to be the same. Which one is it? Wavelength is not the same. What happens when in a freeway when traffic slows down? The distance between the cars gets shorter. Yeah, isn't that true for wavelength, right? So this is going to be shorter. Velocity is going to be slower, but yeah, the waves have to go by you just as frequently because otherwise you'd have like a wave pileup, right? Right? Okay, so the frequency has to be 4.6875 times 10 to the 14th hertz, right? The velocity is going to be somewhat slower. And so I'm going to use the formula N is C over V. So therefore, V is C over N. Right? So it's 3 times 10 to the 8th meters per second divided by 1.51. Is that what it is? Yeah. And you get the velocity is 1.98675. I'll just times 10 to the 8th meters per second. And then the wavelength, how do I do the wavelength? Do I just use V as F lambda? Yeah. Right, so the same velocity, the 1.986755 times 10 to the 8th equals frequency, which is this frequency, same frequency, 4. I'm so sorry. All right. Okay. Times the wavelength. So I'm just going to divide this by my frequency. So divided by 4.6875 e to the 14th. And I get 4.238 times 10 to the minus 7th meters. Right, which would be 424 nanometers. Yeah, but if you write this, that's just fine.
Could you go over number 4, please?
Oh no, there'll be no going over number 4. Only 2 and 3, right? The other way to check your work too is to just go like this. If it's 640 nanometers here, remember it gets smaller, and it gets smaller by the index of refraction. That's a factor, right? So just try what is 640 divided by 1.51. Try that. 640 divided by 1.51. 420, the same exact number, 423.8, right? Right. So 2 ways to get the answer. Yeah. And then number 4, for number 4, you're just doing it, it's a Snell's law, right? Snell. That's 54 degrees. This is N1 is 1.00. Theta 1 is 54. This is N2 is 1.51. And theta 2 is what you're trying to find out, right? So just use N1 sine theta 1 equals N2 sine theta 2, or as IB gives it to us, What does it look like? Or you can use the very unfamiliar to the rest of the world. What is it? It's n1 over n2 is sine theta 2, right? That's what's going to actually be in your data packet. But yeah.
So for the angles, they're always to the vertical, right? It's never going to be...
Always to the vertical,
so
yeah.
If they give us the one that's to the horizontal, we have to just...
Yeah, pay it a compliment, right? Ignore that. And then for the critical angle is, and it's critical that you understand this. The critical angle is an angle, here's the lucite here, right? Okay, you're going from slow to fast, and of course here's this ray of light, and of course it bends over, and the point of no escaping is when you've bent it all the way over and it's escape at 90 degrees, right? Right? So I'm going to call, in this case, N1 is 1.51. I always say wherever it starts is N1 just because I'm a spaz. And if I always do that, then chances are I got it right. And then this theta here is the critical angle, right? Theta 2 is 90 degrees. N2 is 1.00, right? And again, I'm just going to go N1 sine theta 1, right? So 1.51 times sine of the critical angle, right, is 1.00 sine of 90. This always goes away unless you're in radians, and then it's something, something to be calculated then, right? Okay, but you definitely want to be just, that's one, right? And then of course this will be just, right? It's not that it's 1 over some index of refraction. It's that it's the small index of refraction divided by the big, right? And then you take the inverse sine of that. Did we have questions about the first one? Are we okay on the first one? Number 1. Numero uno. Are we good? You could, don't forget to turn these in. You could keep these to study. Let me see if, is this one solved? It'd be nice if it was. Would it be nice? That'd be like a 12-3. Look at that. Lindsay Pozo and those guys. Alex Shrimp. There you go. You could turn them in, or you could keep them and study them. It's up to you. Right, I mean, it's on the website, so you can just go look at it. So. Let's start in about, how much time do we have? How about when Mickey's hand is on the 4, we start Young's double slit and polarization.